Good morning, Dynamics. I've got some new drawing software. Feel the excitement. Okay, so today we want to pivot back to something we did earlier this semester. I want to look at the work. Let's see if that works. Yep. Work equals change in kinetic energy. Method for solving problems. So it's more than a method of solving problems. It's also a different way of thinking about a problem that might be more powerful for that particular problem. So to make this approach work, we need to figure out how to calculate kinetic energy. We know that for an individual particle, kinetic energy is 1/2 mv squared. So this is for an individual particle. That formula works. That's what it is. For a collection of particles, like if you have 3 particles, what you would do to find the kinetic energy of all 3 is you'd add them all together. So you'd add the kinetic energy of the first plus the kinetic energy of the second plus the kinetic energy of the third. So if I have some arbitrary number of particles, I would just put this in a summation symbol where the particles, instead of being just 1, 2, and 3, would be 1/2 mi times vi, and this vi is the velocity of that ith particle squared. Okay, now what if I have a solid object where I have 10 to the 23rd particles? Well, if I have 10 to the 23rd particles, I definitely don't want to add them one at a time, so we want to see if we can manipulate this summation and take advantage of the fact that it's a solid object to come up with a shortcut for finding the kinetic energy. Okay, so to start, what we'll do is we will look at, so I've got some drawing of an object over here on the right. It's got some center of mass G, and I, of course, can write the location of point I compared to our origin as this vector Ri. And that vector is the sum of Rg plus Ri compared to G, which we'd write out like that. You've seen that before. Take a derivative of both sides, and we get that. So I can replace the velocity of point I with that. And I can then take this and expand out that multiplication, and we get 3 terms. Notice the middle term doesn't have a 1/2 because you'd have the 2 times v bar times vig, and then times the 1/2 would cancel out. So I've got these 3 terms. And to see what these 3 terms give for us, I want to look at each term separately. So let's start by looking at term A. Okay, so for term A is the sum of 1/2 mi times the velocity of the center of mass squared. Now, the velocity of the center of mass squared, this term right here, that's a constant. Since it's a constant, meaning it doesn't depend on which particle we're looking at. So that can come outside of the summation. The number 1/2, of course, is also a constant, so that can come outside the summation. And then all that's left inside the summation is the sum of all the individual masses. Now the sum of all the individual masses is the total mass. So term A, after you do the summation, is 1/2 times the total mass times the velocity of the center of mass squared. Okay, so that's term A. Now let's move on to the middle term, term B. Okay, term B has the individual mass times the velocity of that mass compared to the center of mass times the velocity of the center of mass. So think which of those terms is a constant. Yep, v bar. That's a constant, so it can come outside the summation. And now I'm going to write vi compared to g in a different way. So to help with that, look over here. We already agreed that the velocity of point I can be written as the velocity of the center of mass plus the velocity of I compared to the center of mass. So you can replace v bar with VI minus the velocity of the center of mass. And then just distributing through the MI, we get these two summation terms. And now just take a peek up here. It's a pretty fat arrow, but that's all right. By definition of the center of mass, this x bar, we learned this is a relationship from statics. We learned that x bar times the total mass is equal to the location of each individual chunk times their masses. Okay, if you take a derivative of that expression, we get this equation that relates the sum of the individual masses times the individual velocities has to equal the total mass times the velocity of the center of mass. So we take that and replace that. And then on this second summation, the mi term, that's not a constant, but the v bar is. So we pull the v bar outside the sum, and we're left with the sum of mi. The sum of mi is m total, and this then just cancels out, and term b is 0. Wonderful. Now term c. 1/2 mi times vi compared to the center of mass squared. Okay, vi compared to the center of mass, since it's a solid object, let's write that in radial and transverse components. And in radial and transverse components, you have the r dot and then r theta dot. And that r, and it's a little sloppy here, that r is the distance of I compared to the center of mass. So that's the distance I compared to g. That distance does not change. So that r bar, the r dot, that's got to be 0. That's got to be 0 because that distance isn't changing. Okay? And then this squared, this is a vector. Remember, this is a vector that's being squared. A vector squared, that velocity squared, that's the velocity. You could think, is it the cross product? Is this thing right here, could that possibly be meant as v cross v? What would be the cross product of a vector with itself? Don't be shy, say it out loud to yourself. Yep, you're right, 0. So if that was a cross product, you would just get 0. And without proof, the dot product captures what we're trying to do with this vector being squared. So this is going to be a dot product, and so when we do a dot product, we'll just multiply across the top, multiply across the bottom, and we get mi times rig times omega squared. So I get the rig twice, I get the omega twice. The omega is the same. That's the rotational rate of the object. That's the same everywhere on the object. So it comes outside of the sum. And we get this summation of mi compared to g squared. And that, we all have a name for it. That's called the moment of inertia. So the kinetic energy is 1/2 times the moment of inertia times this omega squared. So term A, 1/2 total mass times the velocity of the center of mass squared, plus term B is this rotation term, 1/2 I omega squared. And remember, that middle term went to 0. So the kinetic energy of an object, of a solid object, is composed of its translational kinetic energy and its rotational kinetic energy.